Hello everyone, I'm Kumar here with Anwar, Shreyas, and Vandit, and in this project we'll be modeling AI preparedness across countries using linear regression. In section one, we'll be talking about background and dataset description. Uh, AI has been booming in the past few years, and countries differ widely in their readiness to adopt such technologies. So we'll try to help the policymakers and businesses make informed decisions using this project. Dataset overview, we got this dataset from Kaggle and it is under the name of AI preparedness worldwide. So it has 165 observations and 12 variables, each observation representing an individual country. All the variables in this dataset are numeric except for the country name identifier. So in this table, we see all the variables which we are going to use in our project. AI preparedness index being a response variable, which is the variable of interest, which measures a country's overall capability to leverage and integrate AI technologies. Digital infrastructure, regulation and ethics, human capital and labor market policies, and innovation and economic integration being our four predictive variables. Going down, we also have a small table where we have defined our variables x1 to x4, which we'll be using in our all our plots and analysis in the remainder of this project. Here we can see a scatter plot where we have plotted all the response variables with the predictive variables. We can clearly see a positive linear pattern between these, which is good for our linear regression model. So coming down to another plot, which is a matrix scatter plot for all our variables. Here we have plotted scatter plots with respect to all variables, and we can see a linear pattern in all of them. The diagonal panel here shows the distribution of each variable. Going down, we have also plotted a response predictor and a predictor pairwise correlations. The correlations here are really high, 0.96 being the highest and 0.69 being the lowest. Now, talking about the potential complications, we can have a complication regarding multicollinearity, outliers, regarding not having a constant variance, which we'll be testing in section 2. Now coming to section 2, here is our preliminary model where yi is our AI preparedness index for the country I, and we have beta 0, which is our y-intercept. Beta 1, beta 2, beta 3, and beta 4 are regression coefficients for the corresponding predictor variable. And here ei is our random error term. Going down, we now estimate these beta values using least square estimations. And here is the formula to calculate the B values. We use OLS software in our project to estimate these values, and we get the beta values which are shown in this equation. We also get a high R square and adjusted R square value of 0.998, which means our model explains 99.8% of the variability in our data set. Now, going down to model assumptions, our first assumption is assumption of normality. Here, we'll be using both visual and statistical methods to test this. We plot residual versus the normal scores here. Ideally, it should follow the 45-degree line, but here it is skewed and we can see tails. So we can say that visually speaking, the assumption of normality is not met. Now, by testing it statistically, we calculate the Pearson correlation here, and then we compare it with the critical value at significance level of 0.05. And with this test as well, we come to the same conclusion that the assumption of normality is not met. Now we go to the second assumption, which is the assumption of constant variance. Here we plot the residuals versus fitted values. And as we can see in the graph, we can see that all the points are scattered and random. There is no clear funnel shape. So visually, we can say that there is no uh, uh, visually we can say that the assumption of constant variance is met. Now, statistically speaking, we'll perform a modified Levenet test where the residuals are divided into groups, and then with this test also we come to the same conclusion that the assumption of constant variance is met.
Thank you, Kumar. My name is Shreyas, and I'll be continuing with the next part. Moving on to the next assumption, that is the assumption of uncorrelated residuals. Here we are checking that if the residuals are correlated or not. Usually they're supposed to be independent of each other. So we do this by the visual approach and also the hypothesis approach. In the visual approach, we are plotting the plot residuals versus the index. We see that here we don't see any distinct trends or cyclic patterns, and hence we can say that the residuals are uncorrelated. For this hypothesis approach, we're using the statistical hypothesis or null hypothesis and the alternative hypothesis mentioned here. The test statistics is the Durbin-Watson statistic. It is calculated as shown in the formula here, and uh, the decision rule is as follows: that the d ranges from 0 to 4. A value of 2 shows that it is there is no autocorrelation. A value of 0 indicates there is positive correlation, and a value near 4 indicates a negative correlation. In our case, we see that we're getting an estimated value close to 2, which means that there is no correlation between the residuals here, and hence our independence assumption is satisfied. The fourth assumption is the assumption of absence of multicollinearity. So we are checking if there is any multicollinearity between the predictors, and we do this by using a metric called the variance inflation factor, or the VIF, and it is calculated using the coefficient of determination RJ square, and it can be calculated as shown in the formula here. From our estimates of the software, we're getting the value for the max VIF for our predictors to be 7.88 as shown in the table here. And as per the rule, as this value is less than the max value of 10, we say that we do not have any serious condition of multicollinearity in our model. So hence we can conclude that there is no multicollinearity issue in our model, and the assumption is satisfied. Lastly, the assumption of no outliers is checked in two ways, that is visual approach and also the hypothesis approach. We say that we do not have any extreme values present in our model, that is both the predictor values and also the response variable values. We plot the plot residuals versus Xij, that is the independence predictors, and you can see the four plots shown here on the left. We see that even though there are some points lying on the upper and lower whiskers of the plot, that is, they can be considered as outliers. We say that these are not actually outliers because they can be the deviations. They are natural global inequality rather than the data errors, and they do not appear to be extreme, and they do not need to be immediately removed. Let's test this further using the hat matrix. The hat matrix is calculated using the formula shown here, and the diagonal elements of the hat matrix are called as the leverage values. The rule is that the leverage values, if they are greater than a specific threshold, which is 2p by n, we say that that particular predictor can have outliers present. For our model, we find the threshold value to be 0.0606, and we see that 16 points are greater than this value. And this also matches with the plots that I showed above. Further, to confirm this, we're going to perform the Bonferroni outlier test. And here, the test hypothesis has been mentioned as null hypothesis and alternative hypothesis. We calculate the studentized deleted residual, which is TI, as shown in the formula here. And based on this, the decision rule is that if this TI is greater than the critical value, we reject the null hypothesis. But as in our case, the critical value is less than the student residual is less than the critical value, we fail to reject the null hypothesis. And also the software output also confirms this, as it shows for all the 16 outliers, we see that the outlier flag is false. So we can say with 95% confidence that we don't have any significant outliers present in our model, and the assumption of no outliers is still valid. Moving to the next part, as our assumption of the normality was violated, we can say we can perform the box-Cox transformation, and it is performed on the response variable AI preparedness index, and it is transformed using the formula as shown here. And here, this lambda value is the transformation parameter, which our model is giving an estimated value of around 0.35. And using that, we're going to perform the normality test again. And we can see that the plot shown here on the left has significantly improved from the previous plot that we showed for the non-transformed model. For the normality test, the hypothesis is mentioned above, and we see that our sample correlation is still less than the critical value. So we still reject the null hypothesis and say that it's still not following the normal distribution. So even after performing the transformation, the normality assumption is not corrected. The discussion for this can be such that the AI preparedness index has a restricted score between 0 and 1, and hence this usually forms clusters in such a way that it's very difficult for the box-Cox transformation to be completely fix the normality condition. And we also say that as we have a large number of samples, that is n equal to 165 countries, we say that with statistical theory, the central limit theorem, we assure that with larger sample values, the data will always follow a normal distribution, and hence it can still be considered as a robust model for our analysis, and it is easier to interpret. Lastly, we present our model with all the assumptions which are true and which are satisfied. We say that our complete original model satisfy all the necessary assumptions except for the normality condition. And we have done the box transformation on that. And the complete full model has been presented in the section. Moving on to section 3. Here we are exploring the different interaction terms. The interaction terms are the terms that we can add to our model to add more variability for our predictor variable. Here we plot the plots partial regression plots to check the analysis of the interaction terms. We are plotting six plots here as shown, each being a plot of residuals of the predictor variable versus the residuals of the interaction terms. The first plot is versus x1, x2, the second one is x1, x3, and so on. And we can see that all the plots exhibit a flat trend lines, and there is no significant non-zero slope that is shown, and we cannot see any linear pattern. And hence, we say that these are not significant enough to be added to the model, and hence we do not add any interaction terms. Coming to the part B, as mentioned in part A, we are not adding any interaction terms. We conclude that our full model need not need any interaction terms as it has good variability and it covers good variability of the data. Part C also talks about the same, and it says that we're not checking any correlations for the interaction terms as we do not have any interaction terms, and also we do not perform any standardization on them.
Hello everyone, my name is Vandit, and in this section we will be discussing model search. To determine the optimal subset of predictors for the AI preparedness index, we employed two automated model selection algorithms, backward elimination and stepwise regression. Both methods used a significance level of alpha equal to zero point 0.1 as instructed for the criterion for variable entry and removal. In backward elimination, we begin with the full model containing all potential predictor variables, and iteratively we remove predictor variables with p-value less than alpha. For stepwise regression, we begin with an empty model and iteratively add or remove predictor variables based on the alpha in and alpha out values. We perform stepwise selection with entry and exit thresholds of alpha equal to zero point 0.1 for our tests. Uh, we began the backward elimination process with the full model, which included all four potential predictors: digital infrastructure, human capital, regulation and ethics, and innovation. The algorithm evaluated the statistical contribution of each variable by calculating its p-value. Upon fitting the initial full model, we observed that every predictor yielded a p-value of effectively less than zero point 0.1. Since all variables met the significance criterion, the algorithm terminated without removing any predictors. Consequently, the process confirmed that the original four variable model was already optimal. We had similar results for stepwise regression. The process began with a null model containing only the intercept, and at each iteration, the model evaluated potential regressors based on the following logic with backward check and forward selection. We identified digital infrastructure as the strongest initial predictor and added it to the model. Subsequent iterations added human capital, regulation and ethics, and innovation in order of their residual significance. After each addition, a backward check confirmed that all included variables maintained a p-value below the exclusion threshold of zero point 0.1. Since no existing variables were rendered insignificant by new addition, consequently, the stepwise regression converged on the same set of four predictors as the previous method. The fact that both backward elimination and stepwise regression converge to the exact same subset of predictors provides strong evidence for the stability of our model. This consistency reinforces our earlier findings that all four pillars, infrastructure, human capital, and regulation and innovation, are distinct and essential components of AI preparedness index. We therefore proceed with the full additive model as selected in section 2. We verify that this selected model satisfies the specific statistical requirement for the project, which is significance and multicollinearity. As tested in section 2, we examined the p-values for all four predictors. For each variable, the p-value was significantly lower than the significance level of 0 0.1, satisfying the significance requirement. Similarly, for multicollinearity, we calculated the variance inflation factor. The maximum VIF observed was 7.88. Since this was below the commonly accepted threshold of 10, we confirmed that multicollinearity was not a serious issue in this model. Based on the convergence of both the algorithms, we selected the original first-order regression model as our best model. This model included all the four original predictors without any interaction terms or variable deletions. In section 5, we discuss model selection. Since in section 4, the model search algorithms converged on the full original model, which retained all four original predictors: digital infrastructure, human capital, regulation and ethic, and innovation. Therefore, our primary verification focuses on the full model, which is identical to the preliminary model analyzed in section 2. We verified the assumptions based on the diagnosis previously established, and we came to a conclusion that all the assumptions were valid except the assumption of normality. After evaluating the potential candidates, we have selected full model as the best overall model. We try to justify the explanatory power. The full model possesses an exceptionally high adjusted R square of 0.998. This indicates that 99.8% of the variability in the AI preparedness index is explained by the four selected predictors. All four predictors in this model are highly significant with p-values way below zero point 0.1 threshold. As explored in section 3, the partial regression plots for all six pairwise interaction displayed flat lines. This analysis confirmed that interaction terms did not explain any additional variance. For model stability, the automated search algorithms both converge to this specific set of variables, indicating it is mathematically the most robust combination.
Hi everyone, I'm Inwanigi and I will be continuing with the rest of the section with the final model. So we now have our best model, both backward elimination and stepwise regression converge to the same first order model, confirming that a strictly additive that approach is the most robust one. Our final regression equation, that is y hat equals to negative of 0.0044 plus 0.9615 times r x1 plus 0.9950 times x2 plus 1.0229 times x3 plus 1.0595 times x floor is our final equation. As for the interpretation, the intercept is effectively zero, serving only as the baseline correction. The most critical finding lies in the slopes. Notice that all four coefficients range from remarkably close to 1. That is our infrastructure, human capital, regulations, and innovations, which are also called our beta 1, beta 2, beta 3, and beta 4, are 0.96, 0.99, 1.02, and 1.06 respectively. This proves that AI preparedness is roughly an equal weighted composite, holding other factors constant. One unit improvement in any single pillar results in a nearly proportional 1 unit increase in the total results. Going to the inference and fit, the model fits the data nearly perfectly with adjusted R square of 0.998 and F statistic of an order of 10 raised to the power 4, confirming the global significance. Joint significance here, to verify the stability of the estimates, we calculated the Bonferroni joint confidence intervals. We found that the digital infrastructure lies between 0.88 to 1.04, then human capital lies in 0.91 to 1.08, regulations and ethics between 0.97 to 1.08, and innovation falls between 0.99 to 1.13. Crucially, none of these intervals include zero. This confirms that all four predictors are jointly significant, meaning they all contribute to the model simultaneously without redundancy. As for the prediction accuracy, to demonstrate the forecasting power, we define the benchmark scenario of the scores, that is our H, to be as 0.11 across all categories. The model predicts, that is our point estimate, comes out to be 0.4399, which we got from our software. As for the 95% confidence interval for mean response, came out to be as a range from 0.43842 to 0.4413. The confidence region for the regression line is again from 0.4374 to 0.4423. And finally, the prediction interval for the single new country, we can say, is from 0.426 to 0.452. The fact that our prediction interval is this narrow is because we are spanning only from 0.026 units, validates that our model's high precision in the real world forecasting. As for the final discussion, we'll now be moving to it. That is, this project applies multiple linear regression to quantify the national AI readiness. We established early on that the linear modeling was appropriate based on the strong positive relationship observed in our initial data. Our final model yielded an exceptionally high adjusted R square with an F statistic of order 10.4 and p-value effectively near to zero. This confirms that our four predictors are explaining nearly all the variability in the AI preparedness index. As for the diagnostics, other than our normality, all other assumptions are pretty much satisfied. For the conclusion, our results indicate that the countries become AI ready only when they develop all four pillars together, emphasizing the need for the balanced national strategy. Because every coefficient is close to 1, no single domain dominates. A country cannot simply build servers or ignore laws. The true readiness requires developing infrastructure, human capital, regulation, and innovation simultaneously. As for the future scope, future analysis for us in this scenario could extend by applying regularization methods to test the coefficient stability, or using principal component analysis to uncover latent dimensions of readiness. With this, I would like to wrap our report. Thank you.